All right, good morning, everyone. Welcome to my talk. My name is Marek. I'm Evangelist here at Unity Technologies Singapore. And just quickly about me. Before I joined Unity, I was a programmer working on many mobile, AR, VR, and console titles. So I have quite some experience with developing and optimizing games. I joined Unity in 2016, and as an evangelist, part of my job is meeting a lot of customers. And I see quite many projects, Unity projects of our customers. And this is something I'm going to share with you today. So today's topic is tales, because I'm going to tell you stories that come from real-life project reviews, mainly from a team in Europe. So in Europe, we have a dedicated team of field engineers and solution engineers that visit customers specifically to solve the issues. And the type of issues, they heavily depend on the project and the target platform they work with and the state of a project. So some of the examples could be optimizing mobile performance for a casual mobile game on iOS and Android, or it could be like a very complex PlayStation VR project with compute shaders. And we unfortunately can't disclose the name of the companies and the name of the projects because they need to stay anonymous. But the stories, I can assure you, they are very real. So the type of the problems that we usually see when we visit customers can be split into these sections. So it's mostly the runtime GPU and CPU performance, and this happens when the application doesn't run at the target frame rate because it's CPU or GPU bound. The next would be the patch or build size when application or a patch doesn't meet the requirement size. So let's say some platforms like iOS, App Store or Google Play Store, they have some limitation on your APK size, or maybe you create a Nintendo Switch game and your patch has to be below 500 megabytes. There are quite a lot of limitations that needs to be met. And of course, loading time, we don't want our levels to take for ages to load, and some workflow issues that slow out our development process. So today's plan will be to break this into 5 sections. The first one will be introduction to optimization and profiling in Unity. Then we'll dig into some examples of the CPU optimization, followed by GPU optimization, and after that, also very important, memory footprint optimization. So basically go through some examples that show how we can optimize the memory and reduce its size. And we'll finish with some optimization rules that we should apply in your daily developer's life. So let's start with the introduction to profiling and optimization. So first, let's see what we mean by optimization. And usually, when I talk to optimize something, I mean to modify a project so that a part of it is more efficient or less taxing on the hardware. It could be GPU or CPU. And unfortunately, there are no techniques that will allow you to optimize for all possible aspects. So very often you find that something works very well in one scenario, but with different parameters, maybe on different platforms, on different device, these rules doesn't apply. You can think of it kind of like with a sorting algorithm, right? Some sorting algorithm might apply very well for one scenario, but then in other they will fail. Okay, so what do we want to optimize? We want to achieve a high and steady frame rate. So for example, in films, the standard frame rate is around only 24 frames per second, and the film industry can get away with it because of the camera motion blur. And we actually, in games, we lock our frame rate mostly to 30 or 60 frames per second. And what we should also emphasize is the steadiness of the frame rates, because if we have any dips in the frame rate, let's say we're running at 60 FPS and then our frame rate drops to 30 at some point, our players, they are really going to notice that, and it's not going to be a very pleasant experience for them. The second one, we sometimes forget that the target device that we develop is powered by a battery. So let's say it could be iOS, Android, or Nintendo Switch. So by reducing load on CPU and GPU, we actually allow less power consumption, so it means that the player can enjoy our game for longer. And some of the side effects that come into this one of the higher power consumption is the heating, and device can actually overheat when you run, let's say, full load 60 frames per second on a mobile device. It actually, after a while, your user will feel that device is getting really, really hot. Another thing to think about optimization is the device reach. So you reach more users by targeting lower-end devices. Before, I was working on a mobile game in a mobile game company that was targeting games for children, and very often parents, when they buy mobile games for children, they will not give them the newest iPhone to play with. They will usually give them like a very old phone or maybe a very low-end iPad. So when the child will destroy the device, they will not feel so bad about it. So basically, by decreasing the requirements on your CPU and GPU or offloading your device, you are getting more money because you get more reach and you can reach more users. And we also want to streamline the asset pipeline and authoring workflows to speed up our dev process and make sure we deliver the best quality possible. Iteration time is also very important because if we optimize our asset structure, project settings, we can actually significantly decrease the build times and allow for faster iteration on our projects. And a very important thing to note is that while unperformant code might cause a lot of issues, you should know that optimization involves more than rewriting a code. And what does it involve? It's very often related to reviewing our assets, like texture sizes and formats, compression types, polygon size. And this could be done manually or automatically. You could write some tools to automate this process. Also reviewing the project settings to make sure that we meet the most optimal settings for our target platform. And we could simplify our solutions to make our life easier. For example, create some automated tools for resizing textures to the right size and making sure that every asset that we import to the project has the correct settings. Another question that we want to ask ourselves is, when do we need to optimize? So we always want to make sure that we make informed decisions, and to do that, we need to use specific tools that will help us to gather some information about our game, and this information should drive our optimization efforts. So in programming, there is this notion called like premature optimization. So you don't want to optimize prematurely, meaning that you first need to gather information and make sure that you understand the problem. And once you understand it, then you can actually start optimizing your game. You don't want to guess what's wrong with the game. You want to go into data, see where is the performance bottleneck, and try to fix the issue in an informed way. So let's start with the CPU optimization. And our goal in the CPU optimization is to reduce the stress on the CPU. Very easy, right? So to achieve this, we want to make sure that CPU is the actual performance bottleneck. And another goal is to free up some CPU resources. So you don't stress your CPU to the maximum. You reduce stress on the CPU to allow some leeway to add some other functionalities to your game later. And we can do all of this optimization by optimizing our algorithm or removing some unnecessary work that processor does. And this could be something as simple as changing the order in which you iterate through the 2D array, but it would also aim for zero per frame allocations. So if you allocate your memory on a per frame basis, you are quickly going to run into issues with garbage collection. And unfortunately, the garbage collection algorithm can be quite taxing on your CPU. So per frame allocations are something to avoid. So to avoid any performance bottlenecks on a CPU, we need to first identify the problems, and the tools that we use are these listed on the screen here. So first of all, because we are working with Unity, we want to start with Unity Profiler. If you target iOS, Xcode instruments are a great tool because they allow you to gather even more information about your device and how it performs. On the other hand, many platforms like consoles, they have their own tools that we need to follow to get the maximum possible data. So for the purpose of this talk, I'm going to focus mainly on the Unity Profiler because this is one of the most widely used tools and is actually built in Unity. And it basically allows you to analyze the CPU usage and see what parts of the game are eating your resources. And the second one I want to mention today is many of the projects that I'm going to talk about, they are targeting iOS platform. So on iOS, we want to use the Xcode instruments, which is great. So let's see some real-life examples. So example number one. There is a management mobile game that feels very slow during the gameplay. And this is something that we see very often. We go into the Unity Profiler, uncheck everything except of the garbage collector. And what we see is that we have a picture like this. We have quite a lot of spikes going on here. And what it means is that the garbage collection, in this example, was kicking in every 3 seconds. So if we do this every 3 seconds, if we have this huge spike, it's not ideal. So our hypothesis is that we should see what's happening in the later frame. So after 10 frames, what we see is actually that we're allocating again 400 kilobytes. What about 10 frames later? It's the same story. So what is happening here is that every frame we are allocating 400 kilobytes of data, and if we run our game at 60 FPS, we are going to do 24 megabytes of allocations per second, which is really staggering number. So let's dig into the profiler column, and if this particular view is showing the timeline, the hierarchy view, you can also view your profile in a timeline. And what we can see here is that the game logic update is our culprit, and it's allocating this 400 kilobytes every frame. So all the allocations take place inside this function, and actually if we get deeper, we could see that it's calling this log string to console method that's getting the 377 kilobytes out of it. So most of the problems that we see here, they are caused by this log string to console method. And this is how the method looks like. And as you can see, the problem appears here. So the problem in this particular example was that we are calling the game logic process score, and we are doing some string operations to get the debug to our console. So to fix this issue, what we could do, we could make sure that our build doesn't include any debug log calls, and we could do this by simply getting the platform-dependent compilation statements like hash if Unity editor, or we could use something like conditionals. So I see many studios that are a little bit more experienced with optimization. They will wrap the debug logs inside a separate class, and they'll make a conditional statement like here, enable conditional attribute enable log. And then if you want to see the log in your game, you'd go into project settings and add the define symbol enable log. But then if you publish the application and release it to the public, you would remove this define symbol and none of the debugs will be called. So after all of this, what we can see that we have 0 per frame allocations and no GC spikes. So in this particular example, the problem was solved. The lesson from that is that we should learn how to use the Unity profiler and understand where your managed allocations are coming from. So we saw that we started with a profiler. We saw where the GC allocation is coming from. We identified the problem and quickly solved it. Example number 2 comes from the mobile racing game, this time also from Europe, from the UK. And it was a very fast-paced racing game. So in fast racing simulations, we can't afford dips in the frame rates. We want to have a steady frame rate from the very beginning to the end. And of course, our users are going to notice all the sudden dips in frame rate. So the problem that we had is that when the GC garbage collection kicked in, it was basically stopping the game for like half a second, right? So, and it's not ideal. And it's mostly caused by the managed heap. Like we allocate a lot of memory. It goes, the larger the managed heap, the harder it is to garbage collection to actually clean all the data. And what we usually recommend in situations like this is, let's say you have this racing game. When you go to the racing scene, you should unload all the resources that are not necessary for this particular scene to make this managed heap smaller. Next, we can use some design patterns like object pooling to make sure that we instantiate and destroy all the objects at the beginning and the end of the scene, and we don't do this on a per frame basis. We also want to optimize our frame rate as much as possible. And finally, with Unity 2019.1 and 2, what we can do, we can enable incremental garbage collection. This feature is not enabled by default, but basically what it will do, it will allow you to, instead of cleaning all the garbage in one frame, the work will be spread across many frames. And you can enable it right here in your project settings. Use incremental GC. Okay, so then if we apply this setting instead of this one huge spike, what we're going to see is that we have this work spread over several frames. And in this particular example of this fast-paced racing game, this was something that solved the issue. But let me warn you, the best practice is to optimize your frame time as much as possible before you give some room to incremental GC to do its work. So we shouldn't rely solely on the incremental GC. Let me repeat it again. You have to optimize before you enable the incremental GC. I have some stories about it later. Maybe you can ask me after the talk. So for this particular example, incremental GC did work. Let's move to GPU optimization. So what are the goals of the optimizing GPU? We want to reduce the stress on the GPU as much as possible. Very easy, right? So we want to free up some GPU headroom to allow maybe to run some compute shaders if we have enough resources. And how do we achieve that? We want to minimize the number of the objects that are rendered in a scene. So we only want to render stuff that are in our viewing frustum that our camera can see. And we also want to reduce the number of data that we send to the GPU. So this would be the texture sizes, polygon count, and also expensive shaders, a lot of overdraw. This could also cause some non-performant behavior on a GPU. So for example, for shaders, we could switch them. Instead of using standard shader, we could use unlit shader on mobile to kind of reduce this stress on the GPU. And the tools that we can use, I'm going to recommend definitely the Unity Frame Debugger and Xcode Frame Capture if you are working on iOS. And again, if you work on consoles, let's say Nintendo Switch, PlayStation 4, you will have some different tools that I can't mention on this talk because of all the NDAs. But once you get into console development and you go to development website, you will get all the proprietary tools. So, yeah, this is the frame debugger on the left and Xcode frame capture on the right. And you can see that they are very useful because they give you some useful info about what are the problems in your game. So, example number 3. Our team from Europe visited another customer. They were working on a strategy game on iOS and Android, and they were experiencing some frame rate issues. And after profiling the game with Xcode frame capture, what we saw was warning message that was saying that we are sending too much information to our GPU. And that was meaning this. So basically, once we open the scene, we kind of figure out that there is this object, actually two objects. There are two objects in this view that have 55,000 triangles. And after using tools like a frame debugger, we found out that this object is actually rendered twice. And both of these objects, I'm not sure if you can see. If I wouldn't wear glasses, I wouldn't see it. But this is the same object that has the same amount of triangles, right? So this is again not ideal, and this is what was causing the 55,000 triangles being rendered on a screen. And the Xcode tools, they are very smart, and they allow you to kind of figure it out and warn you that, hey, you are rendering maybe 4 pixels that have inside 55,000 triangles. Not ideal, really. So what do we need to do? Do we need to render so much? Probably no. So our advice is to create some LODs for your assets. So the LOD 0 would be your highest quality mesh, basically your input geometry, and then you should proceed to create LOD 0, which will have a little bit lower poly count, but still high quality. And then for the objects very far away, you could use very low poly count. And if they are like really far away, you can even not render them completely, just call them right away. So after applying LODs, you can see that we are having here 35,000 triangles, which is much, much better. So we went from this to this, which gives us an improvement of around 38%, which is actually quite a lot, just by applying LODs. And we don't decrease any visual quality. We don't lose anything on this. We only gain the performance. So the lesson from this should be that by understanding our requirements and the tools that we can use, we can get almost 40% improvement, all without any observable difference in our final result. Another example, Sprite rendering. So one of our customers, he was working on a game targeting PC and mobile and WebGL. It's actually port from PC to mobile and WebGL. And what they experienced is that they have a very low frame rate after they port the game. And what was happening is that we profiled the game with the Unity profiler, and we saw that we actually spent quite a lot of time on rendering. And the CPU was really busy on sending all the rendering commands, draw close to the GPU. And if you see this green color, it's connected to rendering. So basically all this time was spent on rendering, right? But then the frame debugger revealed to us that what we are doing here is that we are having 3 draw calls. We are rendering 3 tiles, and they generate 3 draw calls, right? But they have all the same material, so they should be rendered in one batch. So what was happening? We saw this message, why this draw call can't be batched is because objects have different materials. But then we came back to the editor, and we saw that, hey, in the editor, they use the same Sprite default material. Where's the problem? What's going on? So when we took a look at the code, what was happening is on start or somewhere in the code, the customer, they were calling the Sprite renderer material. And this particular method is generating a new instance of the material. So every time he was calling this on a tile, it was creating a new instance of the material, and these 2 materials can't be batched together. So a fix would be to, instead of calling the renderer material, we could call the shared material, and then we don't instantiate a new instance, we actually reuse the same one. So After this, we saw that all 3 tiles are drawn within one draw call. So this basically allows us to remove all the unnecessary calls to the draw calls. And the game was successfully deployed to mobile and WebGL without any problems. And one of the side effects was that the standalone version, although it didn't need so much improvements, it helped quite a lot as well. So the lesson that we learned here is that understanding underlying issues, we can get some significant improvements and reduce the draw calls. So that was the last example from the GPU section. Now let's take a look, how do we optimize the memory footprint? So first, what are the goals of the optimizing memory? If the device doesn't have enough memory, let's say it's a patch for the Nintendo Switch, we need to reduce the size of the patch. Mobile data can be actually quite expensive in some countries, right? So to get as much users as possible, you want to decrease the build size, APK or IPA size, to allow users to maybe use mobile data to download your title. And loading times can be killing your game if your assets are really huge. It might take ages to load your scene. Also, if you have more space available later, you can add more content. And you basically avoid hard crashes due to some memory warnings or iOS. And you're basically improving overall performance by shuffling data less often. And this is something I found on Reddit. So imagine that you come back home after time day at work, you turn on your PlayStation, and what you see is that, hey, you need to wait 99 hours before you can start this application. Again, this is not ideal, and you are basically losing players because of your build size. So the tools that we'll use to optimize the memory footprint are going to be the memory profiler and the Xcode instruments, again, because many of the examples, they are based on iOS. So this is how the memory profiler in Unity looks like. Each of these rectangulars, they represent one allocated block of memory. And you can see that there are 145 shaders. And if we select any of these blocks, it will kind of further expand and show us what is inside. So the next example, it was a customer project, and this is actually not very obvious. The customer had like a really large number of materials, and each of the material was using the Unity standard shader. So each material then was assigned to its own asset bundle. And what was happening is that when we did a memory snapshot, it turned out that actually each of these materials, they generated, in the memory snapshot, we saw that they are being included in the memory. So this is, again, not ideal. And the reason behind this is because the shaders are being kind of implicitly included in every asset bundles, and this is just how the asset bundle works. So the solution that we recommend is to download a copy of the built-in shaders from our website. Then we can copy the standard shader into our project, rename it to something like Unite Test Standard Shader, and finally fix all the materials by assigning this new copied shader to the material, and rebuild our asset bundles. So after doing all this work, what we saw is that we have only one block of memory, and it's only one shader instead of this crazy amount of unnecessary work on our memory. And the lesson that we can learn from here is that using the right tools and understanding the internals of the engine, because this asset bundle including shaders was not very obvious, it basically allows us to significantly reduce the memory usage. Let's proceed to the next example. So again, this was another example from Europe, porting a desktop title to mobile. and the game was keeping crashing on the lower end devices. This is a screenshot from Xcode instruments, and just to give you a tip, you always want to stay in this area. You don't want to stay in this area because it means that you're using too much memory and the app will basically crash if you keep doing so. So when we did a memory snapshot, what happened is that we saw that there is this huge 52 megabytes audio clip in the memory. And again, sorry, actually two audio clips. And again, this is not ideal because some of the background music files or maybe ambient sounds, they can be really, really huge. So these two, they were more than 2 minutes each, and they were taking altogether around 50 megabytes of the memory. So when we jumped into the project settings, what we saw that all of them, the preload audio type, sorry, the load type was set to decompress on load. And basically what it does, it loads the entire audio asset to the memory right away. So this is the description from the manual. Audio files will be decompressed as soon as they are loaded. So what we recommend, again, this is also in the manual, this setting should be used only for smaller compressed sounds, not for huge background music. So do we have any other options? There is a streaming option. Again, from our documentation, you can learn that they decode audio on the fly and uses a minimal amount of memory to buffer the compressed data, meaning that we don't load it right away. We just load, use kind of streaming to offload the memory. So this is how it looks like. We go back, change the load type to streaming. And after coming back, what we saw is that it's reduced to 400 kilobytes for both of them. So this is a huge improvement. From 53 megabytes, we went down to barely half megabyte. So this is a staggering 99% reduction in the memory footprint. And the lesson we have to learn from this one is that understanding our requirements can lead to like really, really big improvements. In this particular example, it was 99%. So example number 6. One way to, this is actually really important, one way to automate this process would be to use a script called asset postprocessor. So asset postprocessor, it's a way to write a C# script and detect assets that are being important into your project. And you could name them, let's say, as SFX. You could add a suffix to the name, SFX, BGM, like for background music, sound effect. And then you could detect it in the asset postprocessor and give them different settings depending on the suffix. Okay, so this is the last section, some optimizations rules that we should follow. So the first one is, I want to emphasize this really clearly. So let's just don't assume, let's try not to guess what are the problems. Let's use the right tools for memory, GPU, and CPU to identify where the problem actually is. So profile first. Also, the results that you get in the editor, that might be completely different if you run the same application on a device. So if you profile application in the editor, you know, my laptop, it's much more powerful than my mobile phone. So I'm going to see, hey, I don't actually have any problems on the CPU side. But then if I deploy the same application to my iPhone or Android device, I'm going to see, hey, actually, my CPU is much less powerful and my application becomes CPU bound. So always profile on a target device to get the right data. And this is also very important. Don't try to optimize multiple problems at the same time, because then you don't, let's say you did 2 changes to your project settings and your problem is fixed, and what is happening is that you basically don't know which one of these 2 changes fixed your issue. So always try to fix one problem at a time. And don't just apply optimization tips blindly. Some things might work for your project, but some things might not apply, so always be smart about it. And some advice applied in the wrong situation might actually make your case worse. So for example, when we import textures by default, they have MIP maps enabled. So it means that if you have your camera very close to a texture, it's going to use the lowest MIP map level, meaning that the texture that will be loaded to render this particular object will be the highest quality. But then when you move really far away, it's going to load the higher MIP map level, which will basically get like a lower resolution texture. But applying this particular one will increase the overall texture size. So this is something that will work in games where you have very dynamic camera movement. But if you work, let's say, on the RTS game where you have camera very static on pointing to the scene only from one direction, maybe MIP maps is something that you should avoid, and you should try to optimize the default texture size. Okay, and just to wrap up, I want you to rethink how you approach your solutions. Maybe you should start to use tools like Profiler if you don't use them yet. And you should update fewer things on your CPU and GPU every frame to reduce the overhead, and drawing less stuff is better to achieve better performance and higher frame rates. So that was pretty much for my presentation part, and I think I can take questions from you if you have any. So please free to ask me anything related to optimization. Do we have a mic? Also, if you, can we quickly go back to the slide? I want to share my email. This is my email. If you have any questions, you can drop me an email. I'm also going to be at the Ask the Experts booth outside from 12 to 2 p.m. So feel free to approach me and ask me any questions. If you, yes, we have a question right there.
Thank you, good talk. The Unity profiler.
Yes.
Can that emulate target device, or does it require a target device?
You should go to the target device, and with platforms like Android, you can automatically connect them to the profiler, and then you will see the real data. Because if you profile in the editor, your editor build is not going to tell you much. You should profile on the target device. And for platforms like, let's say, iOS, what I also recommend doing is going into instruments, because instruments are going to give you more details about like how resources are allocated on a CPU, GPU, and memory. So always always profile on a target device. If you think about it, the difference between the CPU here on a laptop and on a phone is huge, and they're going to behave totally differently. All right, any more questions? Yes, there's a question right there.
Hi. In one of your slides, there was an example about the material instancing.
Yes.
With that. I think it's quite surprising that the dot material getter is actually instantiating a new material.
Yes.
I've had issues with this when porting a game to Nintendo Switch, where I had multiple materials being instantiated, and they are all duplicates of one another. What was the fix? Because it wasn't really clear how you actually managed to overcome
All right,
that.
so it was calling the renderer.material. This will return a new instance of the material. So the fix was to call the shared material, because the shared material will not create the new instance.
So you basically enable material instancing for the actual materials as well, and on top of that, you change the API call to shared material.
Yes. But the API call is actually more important, because the GPU instancing is also it's also relevant, but it's slightly different. The fix for this particular example was to get the shared material instead of the material. Yes? Yeah, so it's a while since I profiled the Android device, but what you should be able to do is auto-connect the profiler to your Android. So basically, when you select the development build and auto-connect the profiler, it's going to automatically connect your device to the profiler, and you should see how much resources are used on the CPU and GPU. Yeah. So this is a setting. If you go to edit build settings, it's one of the first settings you will see. There'll be development build, and right under there should be auto-connect the profiler. And also from the profiler, you will have a drop-down menu with I think it's based on the IP address and so basically you can provide the IP address or the device that's connected by the USB cable. All right, so if we don't have any more questions, let's finish here. And any questions later after the session, you can drop me an email or find me at the Ask the Expert booths. Thank you.